Good morning, everyone. My name is Luca Scifoni. I'm a PhD student at Georgia Tech, working on Lunar dust mitigation. And as most of you may know, and as also stated in one of the very first talks in this conference, lunar dust is one of the most significant challenges to lunar exploration because it's adhesive, abrasive, electrostatically charged, toxic. And among the mitigation technologies, one of the most promising is the EDS, the Electrodynamic Dust Shield, which works by generating a non-uniform electric field that interacts with the charged dust particles and swipe them off from surfaces. I have a video here showing how an EDS covered with dust clears off the surface once it's activated. An important distinction is between rigid and flexible devices, because rigid devices already have a high TRL, have been tested on the moon, and can be used to shield, for example, solar panels, thermal radiators, and many types of instrumentation. However, the flexible version still need to be optimized and to be able to conform to more complex surfaces. We have designed several types of EDS. These are copper-based EDS devices where the substrate is made of polyimide, the electrodes are made of copper, and then there is another layer of polyimide that is used as a dielectric coating. The dielectric coating is necessary to avoid any breakdown or micro-discharge that may happen on or between the electrodes. The problem that we have with these devices is that even if they are very cost-effective, easy to design, because they are printed as PCBs, the flexible version may crack after repeated bending because the electrode is made of copper. And this is known to happen with most of the materials that are currently used to realize EDS devices. For this reason, we have realized devices with another material, a nanocomposite material that is CMRGO, chemically modified reduced graphene oxide, that is spray coated and infiltrated on thermoplastic substrate. Being nanocomposite, this material is much more stiff and able to withstand flexibility and mechanical bending. However, the problem that we have is the material compatibility of the dielectric coatings. This research is mostly about the performance of two new types of dielectric coatings that we have applied to the rigid version of the CMRGO-based EDS devices. The first one is polystyrene that is mostly chosen for its high dielectric strength and aiming to reduce the amount of microdischarges. The polystyrene is casted and imprinted in a nano pattern on the EDS surface. The second type of coating is TPFS, that is a functionalization of the electrodes that is used to realize an hydrophobic coating with a lower surface energy and therefore reduce adhesion forces. We have tested the devices under simulated lunar condition in two different vacuum chambers, both able to reach 10 to the negative 8 torr, and both equipped with a dust falling system that is a vibrating device that we use to drop the dust on the EDS during the experiment instead of loading with dust beforehand. In this way, we can test the EDS under more realistic and dynamic dusting conditions. One of the facilities is also equipped with a UV light source to simulate the photoelectric charging of the dust. And this is a more detailed picture of the experimental setup. So the first thing that we tested is how the performance changes with the applied voltage for the different coatings. The plot that you see here is for an uncoated device and is in terms of accumulation factor. The accumulation factor is basically a measurement of how much of the dust that falls on the EDS still stays on its surface at the end of the experiment. And as you can see, when tested at 1500 volts, the uncoated device seems to perform very well with basically zero accumulation. But the problem is that starting at 1000 volts, micro discharges start appearing on the surface, as you can see from the GIF. And this is where the coatings come into play. We have performed the same test with the PS coated and the TPFS coated devices. And when comparing the linear regression, there are significant differences in both the slopes and the intercept of the fits. So first of all, let's compare the blue line, that is the uncoated device, with the green line, that is the PS coated device. As you can see, the accumulation factor is higher for all the applied voltages, meaning that the application of a dielectric coating significantly reduces the performance. But at the same time, with the PS coated device, we are able to test it up to 2000 volts without the appearance of any micro discharge. With the TPFS coated device, on the other hand, we are not able to go above 1500 volts because micro discharges start appearing. But thanks to the reduced adhesion forces, the performance is restored and is much more similar to the performances of an uncoated device tested at 1500. Continuing the analysis, we have analyzed the degradation because anytime a micro discharge happens, there is an erosion of the electrode traces that doesn't let the device, still lets the device work, but the dielectric coatings that are designed to reduce the micro discharges undergo degradation themselves. And this is particularly happening with the PS coating, while the TPFS coating is much more stable under the repeated using. We have concluded the analysis with an analysis of the size of the residual dust on the ADS at the end of the experiments. And as you can see from the histograms that are normalized as probabilities, the only case that stands out is the TPFS coded one, that is the red histogram. And in this case, the reduced adhesion forces make the device much more effective with the larger dust particles. This slide is about the most recent part of this work and is something that is still going on, and it's about the effect of the applied frequency of the signal to the ADS. In the literature, most of the papers use 10 Hz as the frequency for the ADS, but both the experimental results and the numerical model which we designed with a Monte Carlo simulation show that even if it's true that very low frequencies and higher frequencies are not that effective in for the performance of the ADS, it's also true that the optimal frequency is not always 10 Hz and is dependent on the number of phases and on the geometry. In parallel, we have analyzed the performances of the flexible devices. For the flexible CMRGO-based devices, the problem that we have is that the lack of a coating and the appearance of micro discharge limit a lot the voltage that we can apply to the electrodes, and therefore we couldn't test that at very high voltages. Therefore, the performance that we could get is around 50 or maximum 60% of dust removal. However, with the CMRGO-based device, with the copper-based devices that are much more easy to manufacture, and also thanks to the electrostatic simulation that we performed, we realized that to increase the performance of the devices, we should reduce both the electrode width and the interdistance. We are not still able to do it with the CMRGO-based devices because of the manufacturing constraint, but we know what's the path to continue this research to improve the performance. So I just want to conclude with a few key takeaways. We have realized both rigid and flexible versions of the CMRGO-based devices. The uncoated versions perform very well, but they are not suitable for lunar mission because of the appearance of micro discharges. The polystyrene coating is very good in suppressing the micro discharges, but limits the performance, while the TPFS coating results in a much higher dust removal and is also more stable after repeated use. We know from the microscopy that both the degradation and the residual dust size depends on the coating applied, and we have also noticed that the frequency has a less important but still noticeable impact on the performance. For the flexible versions, we still have a limited performance, but thanks to the copper-based versions and to the electrostatic simulation, we know what's the path to follow to improve the performance. And the future work will focus on both improving the manufacturing technique to enhance the performances and to coat the flexible versions. And my colleague Ide, presenting after me, will show you her progresses on this matter. Just want to thank Georgia Tech, NASA Survey, and I look forward to any questions that you may have. Thank you.